Hello, my dear students. This is the second lecture on the course the Real Analysis Second MMTC 202. This is part 2, part 1 of the second lecture. So in this lecture we discuss algebra and some properties of algebra. So first of all, we define algebra. Definition of algebra. So let X be a non-empty set and A be, let's consider A be a class of subsets of X. Then we say this A is an algebra. Then we say A is an algebra if it satisfies the following properties. First property is for all A1, A2 belongs to this class, this should imply their intersection should be belong to A. And second property is for all A belongs to A, this should imply a complement belongs to A. So an algebra is a class of subsets of X satisfying these two properties. For any two members A1 and A2 belongs to A, their intersection should be the member of A. That means this A should be closed with respect to the finite intersection. And second property, for all A belongs to A complement should be in A. That means this A is closed with respect to complementation. So that's the definition of sigma algebra. That's the definition of algebra, not sigma algebra. Sorry. Next, we give some examples of algebra and some meanings. Example. For any non-empty set, X, the class is phi comma X. It's a class of subsets of X. For any non-empty set X, the class is an algebra. Because if you take any two members from this class, the union also sits inside this class. And if you take any member from this class, then its complement is also in this class. For example, phi is there. The complement of phi is X, that's also there. X is there. The complement of X is phi, which is also there. So therefore, this class, which contains only two subsets of X, is an algebra. So, next example is for any non-empty set X, for any non-empty set X, the class power stuff X consisting of all the subsets of X, is an algebra. So this is again trivial. clearly it's closed with respect to finite union, because if you take any two members from power stuff x, so that means these two members are subsets of x. Then their intersection is also a subset of x, so that means the intersection also is the number of power stuff x. So that means power stuff x, which is a subset or set of all subsets of x, is closed with respect to finite intersection. And second property, if I choose any subset of x, then its complement is also a subset of x. So therefore power stuff x is closed under complementation. So that means this power stuff x is an algebra on x. These two algebras are trial algebras. So the next example is let x be not equal to 5 and this cursive f be a family of subsets of x which are pairwise disjoint. Be a family of subsets of x that are pairwise disjoint. Pairwise. So that means this f is a class of subsets of x such that any two members of f are disjoint. And let's take S, which is equal to f, those subsets of x union the 5. Okay. Union 5. So it's consisting of the sets which are pairwise disjoint together with this set, that empty set. Now you can easily verify that S is an algebra. S contains 5. That's the first property. Second property, it's closed with respect to complementation. It's not closed with respect to complementation. You can. It's not an algebra in general, but it's a summary. As phi is there, and if you take any two members from this class, so this then one can easily verify that S is a summary. S is a property 1 is trivial, phi is there. Property 2, if you take any two members from S, suppose A1 and A2 belongs to S, then since this S it contains the members, it contains the subsets of x which are pairwise disjoint. So therefore A1, A2 they are disjoint. A1 intersection A2 is phi, and phi is a member of S. So that means this S is closed with respect to finite union. And third property is important. Third property. So in order to prove third property, we have to show that for any two members of S, we need to show that the set difference of these two members must be equal to finite disjoint union of members of S. So let's take any two members of S. A1, A2 belongs to S. If either A1 is phi or A2 is phi, if A1 is phi or A2 is phi, then clearly A1 minus A2, if A1 is phi, it's equal to phi, or if A2 is phi, it's equal to A1 respectively. It's respectively. So whenever A1 is phi, the difference is phi. Whenever A2 is phi, the difference is A1. So therefore A1 minus A2 can be expressed as a finite disjoint union of members of S. Now second case, if they are not empty, if A1 is not equal to 5 and A2 is not equal to 5, then they are disjoint. So it's like this: A1 should be here. If A1 is here, then A2 should be like this. This is the set X. Set X, A1 and A2, they are subsets of X, and they are also disjoint because this F it contains the disjoint numbers, disjoint subsets of X. So A1 and A2, they are disjoint. Now you can easily verify that this A1 minus A2, then A1 minus A2, it's equal to A1. So it's clearly a finite disjoint union of members of S, which is clearly a finite disjoint union of members of S. So hence S is a semi, but it's not an algebra in general, because if A1 is there, A2 is there, A1 union A0 cannot be in F, because A1 union A0 is not disjoint from A1 and A2. So, but the members of F are pairwise disjoint. Therefore, it's or you can say this: if A2 is in S, then its complement is not in S, because its complement is not disjoint from A1. So therefore, this F is not an algebra. S is not an algebra, but it's a semi. So also you can easily verify that. Also we can easily verify that S is not an algebra. So thus every semi-ring need not be an algebra, because here is an example of semi-ring, which is not an algebra. So now we give one more example, which we have already discussed in lecture 1. It's this: let S be equal to class of semi-closed interval A and B is in R. Then we have shown that this S is a semi-ring. Then S is a semi-ring. But this S is not an algebra, but S is not an algebra. Why it's not an algebra? For instance, the interval 1, 2 belongs to S, but its complement 1, 2 complement, it's equal to minus infinity to 1 union 2 to infinity, which is not a member of S. Because it's not a semi-closed interval. So therefore S is not closed with respect to complementation. 1, 2 belongs to S, but its complement is not in S. So that means S is not closed with respect to complementation. Hence S is not an algebra. That's another example of a semi-ring which is not an algebra. But what about the converse? Can we say that every algebra is just a semi-ring? And the answer is yes, and the proof can be seen in the following theorem. First of all, we discuss certain properties. One more example of an algebra that's actually analog of this example, previous example, in higher dimensions. So one more example. So this semi-ring that we have already discussed previous is very important. The semi-ring discussed in previous example is very important. Is very important, and its importance can be seen. Is very important because it can be used in coming lectures on this course. So also next we give an example of a summary which is the nth dimensional analog of previous example. So we give a higher dimension analog of previous example. Previous example means the summary on real line. Now we define the summary on higher dimension. That's nth dimension. So let's discuss that algebra. That's very important. So that example is also very important for higher dimension. Let A be equal to the product of semi-closed intervals. Product of n semi-closed intervals, n copies of semi-closed intervals. A be equal to this. So to make it clear, so let's take n equals 2. So for n equals 2, this A is equal to the product of these two semi-closed intervals, and this can be shown in the following diagram. Let's take here A1, B1. This is semi-closed interval, and that's A2, B2. That's another semi-closed interval. So what's this cross product? It's actually rectangle. It's semi-closed rectangle. So you can draw perpendicular here on that axis and then draw these horizontal lines. And you can see this product is actually this is closed on that side, closed on that side, and open on this. So this is the product. So for n equal to 2, this A, which is the product of two semi-closed intervals, is actually semi-closed rectangle. So we discussed it. We discussed this set for n actually. A1, B1 cross A2, B2 up to A and Bn. So now, if what's this set actually? If for all I, AI is less than